On August 26, 2026, a catastrophic flash flood struck the Himalayan region near the Nepal-Tibet border. But this was not an ordinary monsoon flood. Evidence indicates that a massive glacier and rock collapse triggered a chain of events that rapidly transformed into a destructive downstream flood. In this video, we explain what happened, why it became so powerful, and what risks still remain. The disaster began high in the Himalayas when part of a glacier and the underlying rock slope suddenly collapsed. The falling mass accelerated downhill as an ice and rock avalanche. As it entered the valley, it mixed with water, sediment, and debris, becoming a powerful debris flow. This surge then entered the river system and developed into catastrophic downstream flooding. The flood began at an elevation of roughly 5,100 meters near the Nepal-Tibet border. It entered the Lhende Khola, then moved through the Bhote Koshi and Trishuli river system. Communities including Timur, Saipru-Besi, Betrawati, Trishuli, and areas farther downstream were affected. The event descended thousands of meters in elevation and altered river channels for more than 100 kilometers. Satellite observations indicate that this event involved more than just melting ice. A section of the glacier, together with underlying bedrock, appears to have failed suddenly. This produced a huge mass of ice and rock moving down the mountain. The exact reason for the slope failure is still under investigation. However, glacier thinning, meltwater, and thawing mountain ground can all contribute to increasing instability in high-altitude environments. Several factors made this event exceptionally dangerous. First, the collapsing material fell more than 1 kilometer through extremely steep terrain. In the upper valley, the moving ice and debris may have reached speeds close to 50 meters per second, or around 180 kilometers per hour. As the flow moved downstream, it collected additional rock, sediment, water, and debris, rapidly increasing its destructive power. The flood dramatically changed the landscape. River channels became wider, banks were severely eroded, and enormous amounts of sediment were deposited across the valley. Some communities were covered by mud, gravel, and larger debris. Roads and bridges were damaged or completely cut, while electricity and other infrastructure were also affected. These conditions made rescue operations and access to isolated communities extremely difficult. The human consequences have been severe. As of August 27, 2026, hundreds of deaths had been confirmed across the affected region, while around 1,000 or more people were still reported missing in different reports. Foreign nationals were also among those missing. These numbers should not be considered final, because rescue operations, identification, and verification are still continuing. Another serious concern is the formation of temporary natural dams. Landslide and flood debris can completely block a mountain river. Water then begins accumulating behind the blockage, creating a temporary lake. If this natural dam suddenly fails, a second powerful flood wave can travel downstream. For this reason, newly formed lakes and unstable debris barriers must be monitored continuously. This disaster is important for flood modeling. A conventional rainfall runoff model can simulate rainfall, runoff, river discharge, and floodplain inundation. But rainfall alone cannot reproduce the initial glacier and rock collapse. Models such as RRI would therefore need an additional upstream inflow or mass flow boundary representing the collapse-generated flood wave. For accurate assessment, hydrology, debris flow processes, river routing, and possible dam break scenarios need to be considered together. The major lesson from this disaster is that Himalayan early warning systems must monitor more than rainfall and river levels. Satellite imagery can detect changes in glaciers, slopes, and mountain lakes. Seismic and ground sensors can identify sudden slope failures. River gauges and cameras can detect rapidly rising water. Most importantly, warnings must be communicated quickly across borders and reach downstream communities before the flood wave arrives. The information presented here is based on reports and analysis from trusted sources, including